Okay. So in this cycle, there is a chain you can follow that here the heat addition process is constant pressure instead of constant volume. The remaining processes are similar or identical in comparison with the Otto cycle. Only thing is the heat addition process that is different. So that can be attributed to the actual cycle for which the diesel cycle is the ideal cycle. That means behind all these ideal cycles, there is one actual cycle, which is basically actually used in engines, or engine basically runs on those cycles. Engine, uh, they operate on these cycles, actual cycles, but ideal cycles are the ideals for these cycles. Now, the differences are attributed to the actually the property of the fuel, because you see that during this process 2 to 3, it is a combustion process, basically, physically or actually. In reality, this is a combustion process, and combustion is dependent on the fuel characteristics. Okay. For a petrol engine or for SI engine, the fuel that is used is mainly petrol. Petrol actually in ideal condition or in general, it is called gasoline, and the simple or simplified version of that is denoted with octane. And this is a volatile fuel, and this can mix well with air, and therefore during combustion the fuel and air is well mixed and the combustion will be very fast. So that very fast is actually idealized as a constant volume combustion, because it is well mixed already and therefore it is ready for combustion. So once the spark plug is firing the charge, it will immediately go for combustion, as if, although practically there is nothing like immediate combustion, there will be definitely some piston movement during this process. Whatever small that time may be in order of milliseconds, but there will be a time duration for the combustion, but it is idealized as instant combustion or constant volume combustion. But the fuel that is used for diesel engine, that is not so volatile, and there will be some time which is much more compared to the time required for combustion for the petrol or gasoline or octane. Therefore, this process is idealized as a constant pressure combustion instead of constant volume combustion. Now, actually, before combustion, the fuel must be mixed with the air. That we have to understand. During our discussion on the thermodynamics of chemical combustion or chemical reaction, we have seen that fuels and air will burn in gaseous state. Therefore, when there will be combustion, the fuel must be mixed well, because you see that these fuels, that is petrol, diesel, these are actually available in liquid form, and liquid will not go for combustion. So liquid must be evaporated and made to gaseous state and mixed with, and then it will be mixed with air, and therefore after that mixing only there will be combustion. So that mixing process requires basically two processes. One is called the atomization, another is called the evaporation. Now, atomization does not literally mean that the fuel will be broken to atoms. Okay, that should not be confused. That should not be considered. That fuels will be basically broken into its atoms, because fuel means this is the compound and atoms are actually for the elements only, right? So when the fuel will be atomized, it means from a larger droplet or from a large liquid matter, it will be broken into small liquid drops, smaller and smaller liquid drops. So from a gross diameter liquid, it will be made with very smaller diameter liquid drops. That process is called atomization. Okay. Now that atomization will take place under an expansion process. Means expansion means what? Pressure drop will take place. So in the injector, fuel injector, there will be basically very high pressure, and in the combustion chamber, comparatively there will be low pressure. So when the fuel comes from the injector high pressure to the low pressure cylinder, and that means from the injector at high pressure to the cylinder at comparatively much lower pressure, then the fuel will break into droplets. And that process is called atomization. Now, once the atomization is done, that is also in liquid form. The fuel droplets, although it is very small in size, but it is basically in liquid, still in liquid form. Now that has to be evaporated because the liquid will not go for combustion. The fuel will go for combustion only in gaseous state. So evaporation is also important. And evaporation, for that evaporation, you need some enthalpy of evaporation involved. Therefore, there will be some phase change. Okay. So initial one, that is atomization, is a physical breaking, but evaporation is a phase change process. So it will absorb some thermal energy, and therefore the temperature may drop of the surrounding. So accordingly, we have to ensure that the surrounding is at high temperature. So evaporation is faster. So you have to understand that when the combustion is actually going on in an engine, the engine is running at in the order of say 1,000 RPM, say 1,000, maybe say 1,000 or 2,000 or 3,000, like that, say 1,500 or 2,000, 3,000, like that, or order of RPM. Then the time required, or the time available for this evaporation, all these are very small, in the order of millisecond. You can simply calculate for a four-stroke how can what will be the actual time that is available for all these processes. So that will be of the order of millisecond, means maybe say 20, 30 millisecond, like that. So therefore, it is really very small time, and we have to ensure that the fuel must be evaporated properly so that the combustion is proper. Otherwise, what will happen? The fuel will not burn, and there will be unburned fuel, and there will be many issues, problems related to that. So first of all, there will be basically inefficient combustion, and therefore the power output from the engine will decrease definitely, because fuel is supposed to give you the power, but fuel is unburnt, fuel is not combusted properly. Therefore, there will be insufficient, that means inefficient power production. Power production will be reduced. Moreover, there will be pollution related to the unburnt hydrocarbon, etc. So therefore, we have to ensure that evaporation is proper. After the evaporation, there will be combustion. So during this process, that is the evaporation, the atomization, that is physical breaking, and then evaporation, that is phase change. So during this time, the piston moves. Okay, that we have to understand that during the process, the piston moves from 2 to 3, and there will be some combustion initiated. So during the spraying of the fuel, and there will be some accumulation, etc., of the fuel, and means the combustion will be initiated. So combustion will take place from 2 to 3, but during that process, the piston also moves. So due to this type of fuel characteristic, that is the slow, that is evaporation, etc., means due to the less volatility of diesel. Petrol is highly volatile, so it will almost immediately mix with air, and it will be ready for combustion. But diesel, for that, it is not so fast. And during this process, 2 to 3, the piston moves, and therefore whatever pressure rise is taking place due to the combustion process, the expansion made by the piston will try to normalize that pressure increase. Therefore, the pressure will remain constant during the 2 to 3 process. So that is the idea behind constant pressure combustion. That is, although you have to understand that this is idealized one. Actually, there will be some pressure variation, obviously. But theoretically, we are considering that during this process, the pressure rise is taking place due to combustion. There is burning of fuel. It will try to increase the pressure, but the piston movement will try to reduce the pressure. And therefore, there will be a balance of pressure and the pressure will remain constant during this process 2 to 3. So this is heat addition process at constant volume. That is the idea behind this. And the other processes like isentropic expansion, constant volume heat rejection, and isentropic compression, these are basically same. Okay. Now, the names of the processes are mentioned here, so you can read it. Now, the same diagram is drawn in the TS plane. So you can see 1 to 2 is isentropic. So there's a vertical line. 2 to 3 is constant pressure combustion. It is a line. It is shown here as straight line, but actually it is not a straight line. So it's for very simple analysis. It is shown with a straight line. It will not be a straight line. So here it is considered that for this, it is considered that the specific heat is constant. Okay. So it is coming to be straight, but actually the specific heat changes with temperature and therefore it will not be a straight line. Okay. The line slope will depend on the temperature and the specific heat. As you have studied in thermodynamics, basic thermodynamics, the slope of a constant pressure line in the TS plane is del T del S at constant P is equal to T by Cp. And that you can get from the TdS relation easily. I will advise you to derive all these yourselves so that your understanding will become deeper. So del T del S, why it is this, why is that, like these things you can do yourself. So that depends on the calculus, the understanding of calculus and application. Okay. So T by Cp, Cv. So if it is constant volume, that is slope of the constant volume line in the TS plane is equal to T by Cv, and slope of the constant pressure line in the TS plane is T by Cp. Okay. Now you see that this depends on temperature and the specific heat. So if the specific heat is constant, then with temperature it is a linear variation. Otherwise, you see that if the Cp also changes with temperature, then it is not linear, it will be non-linear. Another thing is that you have to follow that this is the constant pressure line and this is the constant volume line. So slope are definitely different. Slope of this line and slope of this line. You can see which one will be more. Say if I mark, this is a 1 and this is a 2. Then you see that as Cv is less, therefore the denominator is less, therefore the total ratio will be more, therefore 2 is greater than 1. For a particular value of temperature, that means at a particular temperature, the slope of the constant volume line is more than the slope of the constant pressure line in the TS diagram. So 2 is greater than 1. Therefore, you see that constant volume line is steeper compared to constant pressure line. So that you have to clearly draw while drawing the TS diagram for diesel cycle. That should be drawn. You should not draw like a parallelogram like that. Okay, that shows your understanding that you have understood properly that constant pressure line is having a less slope compared to constant volume line. That you have to first understand, appreciate, and then you have to draw it properly. Okay. So there are differences, obviously. Another thing that we have to just mention that for the diesel engine, the compression ratio is much more that can be used, or the fuel that is used actually that can withstand high compression ratio. So it depends on what fuel we are using. For a gasoline engine, we use generally octane, which cannot withstand that high compression ratio. It will withstand only from about 7 to 10 or 12. In the last class, we have shown. For diesel engine, the diesel fuel actually, it can withstand a high compression ratio. It will not go for severe, means it will not go for knocking in that order. Therefore, we can put the diesel engine to use at high compression ratio. That is why the heavy vehicles can be in heavy vehicles, the diesel engines are used because it can withstand high compression ratio. And we know that with compression ratio, the work output and the efficiency increases. Although we will show that for the same compression ratio, the Otto cycle is having higher efficiency compared to the diesel cycle. But since diesel cycle can be used at a higher compression ratio, so considering that point in mind, the efficiency in that order of compression ratio will be much higher in comparison with the Otto cycle. So that is one important point to be noted. Next is the efficiency calculation of diesel cycle. So we can see that this is the PV diagram of the diesel cycle and this is the TS diagram. We have redrawn it. Now, what is efficiency? Again, efficiency is same as W net divided by Q in. So basic definition we have to always remember. Okay. So what is the definition of efficiency in the last class I told? Basic definition of efficiency. Note this forever. Efficiency is equal to desired effect divided by energy that costs. Now, this desired effect, this definition applies for even refrigerators, air conditioners, etc. This definition applies to COP also. That means this is efficiency. This definition is applicable to COP also. So COP of, say, for example, refrigerator or heat pump is same. Desired effect by energy that cost. So we can show it or verify it during our discussion on refrigeration cycles. So this is the definition. And desired effect, what is that? Desired effect is W net. And the energy that cost is Q in, that is heat input. So that is the thermal efficiency. Yeah. And this thermal efficiency we call actually as indicated thermal efficiency. Indicated thermal efficiency. As this W net is basically indicated, that means rate of this W net. So W net dot rate of work output, that is called indicated power. Indicated power or IP. So that is the definition of the thermal efficiency or indicated thermal efficiency. Okay. Next, W net is what? What is W net? Again, we will apply the first law. That is W net is equal to Q net. first law for thermodynamic cycles. So W net is equal to Q net, and Q net we know there is a heat addition and there is one heat rejection. So Q in minus Q out. Therefore, thermal efficiency of the diesel cycle is what? Is equal to 1 minus Q out by Q in. As we are doing this again and again, we have just write it. We have just written it quickly. Okay. Next, the thermal efficiency is this. Therefore, what is Q out for the diesel cycle? Now, let us draw the diesel cycle here once again. So, or we can show it in the diagram there. See, what is Q out? Q out is for this process. And Q in is for this process. What is this process? 421 is constant volume process. And 223 is constant pressure process. Now, if we apply the first law for this, remember that this is a constant mass system, a control mass system. So, for the constant volume process, Q is equal to basically delta U for constant volume process. And for constant pressure process, Q is equal to delta H. And this delta U is equal to CV dt, CV delta T for ideal gas. And this delta H is equal to Cp delta T for ideal gas. And this delta T means what? This delta T means basically for constant volume process, this is delta T. So T4 minus T1. So CV T4 minus T1. And this is delta H is equal to Cp delta T. For this process, it is T3 minus T2. So we are considering the magnitude only. We have to understand that. So Cp delta T, what is that? Delta T is T3 minus T2. Okay, so for one, this is Q basically heat rejection. So it is Q out. And this is Q in, constant pressure heat input and constant volume heat rejection. So that must be understood. So therefore, this Q out is equal to Cv into delta T, that is T4 minus T1. That you can see Cv multiplied by T4 minus T1. Q out is equal to, and Q in is equal to delta H, that is H3 minus H2 is equal to Cp into T3 minus T2. Okay. Now here you see that, therefore on the top you have Cv into sorry, it is erased. So this Q out is equal to Cv T4 minus T1 and Q in is equal to Cp T3 minus T2. So on the top you have Cv, in the denominator you have Cp. So Cv by Cp is equal to 1 by gamma or 1 by K. So 1 minus T4 minus T1 divided by K into T3 minus T1. So that is coming from that. Again, this is 1 minus, what we are doing is we are taking T1 from this out, and here we are taking T2 out, as we had done for Otto cycle also. Similar things we are doing, because some processes are similar, therefore we can go for similar calculations or similar arrangements or similar manipulations. Therefore, it is this one. Okay. No, so now let us write it. Therefore, 1 minus 1 by gamma, that is coming from that one. So it is T1, it is T2 by T1 minus 1 divided by T2. So it is T3 by T2 minus 1. Sorry, it is T4 by T1. I'm sorry. T4 by T1 minus 1 by T3 by T2 minus 1. Next, what is therefore to be calculated is the ratios. So as we have done in the earlier one, what is T1 by T2? That we have done already. 1 by R to the power gamma minus 1. Where from it is coming? The compression process is P1, V1 to the power gamma is equal to P2, V2 to the power gamma. So that will give you P1 by P2 is equal to V2 by V1 to the power gamma. Again, P1 V1 by T1 is equal to, from this you will get a ratio of P1 by P2. So that is V2 by V1 multiplied with by T1 by T2. T1 by T2. And this is equal to this one. So this is what? V2 by V1. V2 by V1 means 1 by R to the power gamma. And this one is equal to 1 by R to the power and 1 by R multiplied by T1 by T2. Therefore, T1 by T2 multiplied by 1 by R is equal to 1 by R to the power gamma. Therefore, T1 by T2 is equal to 1 by R to the power gamma minus 1. Okay, so T1 by T2 we have already calculated for Otto cycle. So this is known. Now, we will try to understand what are the other relations T4 by T1 and T3 by T2. T4 by T1 and T3 by T2 that we have to determine. So the 2 to 3 process is constant pressure process. 2 to 3. Let us draw it again. So 1, 2, 3, 4. 2 to 3 is a constant pressure process. Therefore, for this, we can write constant pressure. That means what? If I write the equation of state, so it will be basically P2 V2 by T2 is equal to P3 V3 by T3. Now P2 is equal to P3. Therefore, we can write that V2 by T2 is equal to V3 by T3. So from this, we can determine what is T3 by T2 is equal to V3 by V2. T3 by T2 is equal to V3 by V2. Now here, there is another ratio called the cutoff ratio. The volume at 3 divided by volume at 2. So that is called cutoff ratio. Cutoff ratio, we denote it with RC, cutoff ratio. And this is basically volume, you can say loosely basically. Volume after combustion? Divided by volume before combustion. Okay. So that is the ratio is equal to V3 by V2. So that can be also called the cutoff point at 3. So like fuel supply or fuel injection cutoff, like that. So V3 by V2. Again, therefore, this V3 by V2 is equal to therefore RC. Therefore, T3 by T2 is equal to RC. This one is RC. This one is RC. This one we have already determined, that is 1 by R to the power gamma minus 1. Now our task is to determine what is T4 by T1. T4, T1, you see that this is a constant volume process. So again, we can write for constant volume process. T4 by T1 that we have to determine. T1 by T2. T1 by T2 is equal to 1 by R to the power gamma minus 1. Now this process 3 to 4 is similar to that 4 to 1. Sorry, 2 to 1 or 1 to 2. So for this also we can write that T4 by T3 is equal to what? T4 by T3 is equal to, here it is T1 by T2 is equal to V2 by V1. So it is basically therefore V3 by V4. That one you see that T1 by T2 is equal to basically T1 by T2 was coming as V2 by V1 to the power gamma minus 1. So therefore it will be T4 by T1 will be this to the power gamma minus 1. In the same way, isentropic process, therefore we can write this. Okay. Now you see that 1, 2, T1 by T2 we know, T4 by T3 we are trying to determine. Now V3 by V4 we can write what? V3 by V4. Because you see that V3 by V4 there is no such ratio as defined. So we will try to calculate this V3 by V4 in terms of some volume ratio that we have defined already. So we can write V3 by V4 as V3 by V2 multiplied with V2 by V4. You see that I am just splitting this ratio as a product of two ratios. Simply you can cancel this V4, V2 from the denominator and numerator. It will remain as V3 by V4, but this new representation will basically help us. How? You see that V3 by V2 is already defined, V3 by V2, that is RC. And what is V2 by V4? V4, you see this one, V4 is nothing but V1. Therefore, we can write this as, what is V3 by V2? It is RC. And what is V2 by V4? That is V4, V2, I'm sorry, V1 by V2 by V1. The quantity V4 is equal to V1. Therefore, you can write V2 by V1 to the power gamma minus 1. Therefore, this is what? RC multiplied by 1 by r, 1 by r to the power gamma minus 1. I'm sorry, this is not gamma minus 1. This is 1 by r whole multiplied whole to the power gamma minus 1. Okay. So therefore T4 by T3 is equal to this. Therefore, our target was to calculate T4 by T1. So T4 by T1 means what? So we will try to calculate this. T4 by T1. T4 by T1 is equal to T4 by T3 multiplied by T3 by T2 multiplied with T2 by T1. So this quantity we know already. T4 by T3 we know, and T3 by T2 also we know. This quantity is already known. You see that T4 by T3 is already known. T3 by T2 is already known. Where? This one. T3 by T2 and T2 by T1 is also known. Therefore, we can write T4 by T1 is equal to T4 by T1 is equal to T4 by T3. T4 by T3 is equal to RC by 1 by R, or RC by R simply, to the power gamma minus 1. T3 by T2, what is that? T3 by T2 is equal to simply RC. And T1 by T2, T2 by T1 is equal to R to the power gamma minus 1. Okay. So you see that this is R to the power gamma 1 by R to the power gamma minus 1, and here it is R to the power gamma minus 1. So they will cancel. So it will become very simple. Although initially it looks very complex, but it will cancel with this one, because here it is R to the power gamma minus 1 and it is R to the power gamma minus 1 in the numerator. So they will cancel. Therefore, it will be is equal to RC to the power gamma minus 1 whole multiplied with RC. So it will be basically RC to the power gamma minus 1 plus 1. So it is RC to the power gamma. So therefore, we can write here in this relation, it is 1 minus 1 by gamma. T1 by T2 is what? 1 by R to the power gamma minus 1. In the numerator, we have T4 by T1, that is basically RC to the power gamma minus 1. And in the denominator, we have T3 by T2. T3 by T2 is RC. So RC minus 1. So that is the expression for thermal efficiency of the diesel cycle. So let us rewrite that. So thermal efficiency of the diesel cycle is what? 1 minus 1 by gamma whole multiplied by R to the power gamma minus 1 multiplied with RC to the power gamma minus 1 divided by RC minus 1. This is the thermal efficiency for the diesel cycle. And what is the thermal efficiency for the Otto cycle? That we have already written, this one. This one. So you see that there is a common part in the diesel cycle and the Otto cycle thermal efficiency. And there is a part which is a factor with that. So thermal efficiency of the Otto cycle, if we write, thermal efficiency of the Otto cycle is equal to 1 minus 1 by r to the power gamma minus 1. So here you can see that if we just rewrite it to compare, so it will be 1 by r to the power gamma minus 1 multiplied by 1 by gamma, it is. So you see that this part is a factor which is multiplied in case of diesel engine. And we can understand that from analysis that this is greater than 1 for the ratio. This ratio, all these ratios are greater than 1. So this, if we expand this, then it will be r to the power rc to the power gamma minus 1 divided by gamma into rc minus 1. That will come to be basically greater than 1. This ratio is greater than 1. Therefore, let me show it. Yes. So this part, this is greater than 1. Gamma is greater than 1 and RC is greater than 1. So this is greater than 1. And therefore, for the same compression ratio and the value of specific heat ratio, the thermal efficiency of the Otto cycle is more than the thermal efficiency of the diesel cycle. This is more than 1, therefore the negative part is more, therefore it will be less compared to the Otto cycle. That can be shown if we go for expansion, then it will be coming as 1 plus some positive quantity. If we go for expansion binomially, then it will be basically 1 plus some quantity which is positive. And that will be basically giving you that this is greater than 1. Okay. So we are stopping here today.